And the thin lenses is like the core component in many optical devices later on we study. So if we understand well about the properties, about the principle of creating the image formed by the thin lenses, and then the next sections you will feel very comfortable and easy as well. So showing you here in these figures is an example of the thin lenses. And typically this one is a converging lens. Yes, the converging thin lens. So why it is named converging lens? And later on you will deal with the diverging lens as well. So why, right? So it comes from the properties of that type of lens. For example, here you see in this figure, the parallel rays of light coming to this lens, and then the refracted ones converged, right? Converged at this point. So that's why we call here this point is a focal point. And we see that there is a lens. So it consists of two spherical surfaces. So two. That's why in this case you also have like some special points in which they called the first focal point and second focal point. So we have here, pay attention, F1 is the first focal point and F2 is the second focal point. And these focal point, their names come from the way that the light focuses. If you have the incident rays of light to this lens, they are parallel like this. After passing through this lens, they converge at this point. So this point is called the second focal point. And here, if you have the incoming rays to this lens, and they come from this point, and then the outgoing rays are in parallel. So the point we just mentioned is the first focal point. So we will deal with first the concept of the lens. So a lens is an optical system with two refracting surfaces. So you have two refracting surfaces, and this can create a lens. And a thin lens, you also have the thin lens, and normally during this chapter, we deal with the thin lens only. So a thin lens, it has two spherical surfaces, you see here, which are close enough together, and that the distance between them, or we say the thickness of the lens here, can be neglected. So normally you will also denote the thin lens by only a line like this one. And then you draw also the two arrows at the two edges, right? So in this subject, we will only deal with the thin lens only, okay? So now we will move to the properties of a lens. So some properties of a lens we need to consider. First, for a converging thin lens, like what we see in this figure, if a beam of rays parallel to the axis, we see the axis here, and I also want to mention with you the axis, in fact, it will connect the two center of curvature. You have two spherical surface here, so you got the first center of curvature for this first surface, and also there is another, the second center of curvature here for this sphere as well. And this line is called the axis of the lens. And also there is one point which is here, which is the so-called the center of the lens as well. So if a beam of rays parallel to the axis, and then it passes through the lens, you see, if a beam of rays parallel to the axis passes through the lens, and then the ray converge to a point F2, you see here. So normally we will draw the rays of light until this line, the rays coming to this line, you see. So we draw this until this point, and then reflect here. This rays to this point, and reflect here as well. This line, we draw this. And also you can use that line for illustrating a lens as well. So the rays converge to a point F2 here. And if a ray is passing through F1, so they emerge, you see, emerge from the lens as a beam of parallel rays. So these 2 points are called first focal point and second focal point. So the first focal point related to the incoming rays, and the second focal point relates to the outgoing rays. So that's why the order you see F1 and F2. So F1 you see for the converging lens, it is in the same side with the incoming rays of the lens. If we choose the lens like the boundary, and then the first focal point and the incoming rays at the same side. So that's why the focal length F here, you see F, the focal length is positive because it's real. And the F2 is real as well because the outgoing rays gather here, reality, right? So that's why you have the focal length for the converging lens is positive. So F1, F2 are called first and second focal point. And F, the little f here, this character F, denotes the distance from the focal point to the center of the lens, which is called focal length. So the center of the lens, here you have C1, the center of curvature. C2 is another center of curvature elsewhere. And then the center point is called the center of the lens. We got here. Okay. And the line connecting the centers of curvature of 2 spherical surfaces is called optic assist. So they are the properties of the lens. Please keep in mind them as well. Focal point, focal length, optic assist, the center of the lens as well. Okay, good, right. Everything is well recognized because you already studied them before. Now we will move to the formation of an image by this lens. So we will consider an extended object here. And here we have a converging lens. And then we will find the image. So you see this line passing through the center of the lens O. We see O here is the center of the lens. And the height of the object PQ with this cap direction. You see this arrow shows the direction of the object here in this direction. So Y is positive. And in order to find the image, we need to draw at least 2 rays of light, right? So the first one, if you draw QO, so it passes through the center of the lens and then it goes straight. The second ray you draw is parallel to the optic assist. The optic assist, so you have 2 spheres, 2 spherical surfaces here. So the center of curvature, the first one is here, for example, here, like this one. And the second one is here. Normally we say here is the first surface because it's closer to the object. And here is the second one because it is in this side. And then we have here the optic assist, which passes through the 2 center of curvature. And O is the center of the lens, which is the center of the line connecting between the 2 centers of curvatures as well. So you draw the ray, which is parallel to the optic assist. So it meets the lens, and we will draw until this line. You see the line here. So the outgoing ray passing through the focal point. So F1, F2 are 2 focal points of this converging lens. So for the converging lens, the first focal point is here on this side, in the same side with the incoming rays. And the F2, the second focal point is located in the same side with the outgoing rays. And both of them are, we say, positive and real. So the focal length F are positive, okay? Is positive, sorry, the focal length here is positive. So this rays when go passing through the second focal point. So the 2 outgoing rays, AF2 and OQ prime, they intersect at this point. And this we can find the image Q prime of Q. And you just draw the projection of this line, and then you got P prime. So P prime Q prime is the image of PQ, and the height of the image is Y prime. So if you can draw, and then you can see immediately the properties of the image as well, in this case, right? So the image here, you see that the two refracted rays intersect, truly intersect. So you have the image is real. It is first property. So for this case, for example, let me place the chat box. I want to move to the chat box to show you in this case, the image is, we see a rear, right? And we see the direction of the image, which is inverted to the object, so inverted. And the size, about the size, which can be like more or less, we see this is like, it seems to be a special case in which the object is very close to 2f, very close to 2f, the distance s. The distance s from the object to the lens. So it is OP from this point to the center of the lens. So it is S, and the distance from the image to the center of the lens, OP prime, is S prime, which is the image distance. So, and I mentioned here maybe, because they don't mention the values of S, but maybe S is around 2f. So larger than a little bit, so we can conclude here, I mean, at a glance, that the image is smaller than the object. So like when you draw, and then you can easily conclude that it's just like qualitatively, right? In order to calculate and something, you need the values for S and F as well. So here, S and S prime are the object and image distances. So the distance from the object to the lens will be identified by the distance from the object to the center of the lens. Similarly, for the image to the center of the lens as well. Y and Y prime are the object and image height, you see. So, and also please pay attention to the direction. If it is in the vertical one like this one, so it is positive for Y. Here, in this direction, that means Y prime is negative. So Y prime negative, and last time we also have a so-called lateral magnification. M equal to Y prime divided by Y, the so-called lateral magnification. So in this case, M is also negative. That means the image is inverted, you see. And in order to confirm that it is larger or smaller or equal with the object size, we need to see the absolute value of M, right? It will help us conclude the size of the image, like larger than or smaller than or equal to the size of the object. So that's why we have here the lateral magnification. And the later sessions, if you already read the lecture note or the textbook at home, you see that some other optical devices, also another type of magnification will be used, which is big M here, the angular magnification. However, we will deal with this later on, okay? Now we just stop at the lateral magnification. So in order to find the image, we draw QA, which is parallel to the optic assist. So it passes through the second focal point, F2. And here, pay attention, we are dealing with the converging lens, okay? QO, Q prime passes undeflected straight through the center of the lens. It is obvious, right? Okay. And then we will see P prime, Q prime, which is the image of PQ. And in order to see the relationship between the object image distance and also the focal length, we will use a geometry. That's why we are in the topic of geometric optics. So the geometry is used in which we will consider the two similar right triangles, PQO and P'Q''O, because these two right triangles related to the distance S, the object distance, the values of S prime, the image distance, as well as the height of the object Y and the height of the image Y prime. So that's why we will consider the relationship between these two right triangles. So they are similar, so you can use some kind of ratio, right? So you see Y prime over Y, P prime Q prime over PQ will be equal to P prime O over OP. So here you got S prime over S. However, S and S prime in this case are both positive because the image and also this object, for sure, if we draw like this one, they are both real. That's why, yes. So we have the negative sign here. Because Y prime is negative, Y is positive, and S prime are both positive. That's why we need this kind of sign, -1. So you got this one. And now we look to others right triangles as well, OA F2 and P prime Q prime F2. So there are two similar right triangles. So you see here this angle beta, which created by the optic assist and the rays of light which pass through the second focal point here, the outgoing rays. And you have also alpha, which created by the optic assist, and the rays come from the object Q to the center of the lens. So this alpha shows also this object, and beta shows also this image you see here. So we have Y prime, P prime, Q prime over AO, which is also Y prime over Y. And pay attention, you need also this minus point here or negative sign, equals P prime F2, which is equal to S prime minus F over OF2, which is F. And then from these two equations, you can deduce the relationship 1 over S plus 1 over S prime equal 1 over F, which you already knew long time ago, right? From the secondary to the high school as well. So you know that's formation. And here we do the small proof for that. Okay, so you understand this comes from the geometric optics. So that's why we're dealing with the geometric optics here. And this expression shows the object and image relationship by a thin lens. Okay. Here we consider the converging lens, but for sure it works for the diverging lens as well. We consider this case for the ease, and also you can prove that using the diverging lens. Only the difference that you have like some new negative sign as well. And we have also the lateral magnification for the case of thin lens. So original formula for the lateral magnification M is defined by the ratio of the height of the image and the height of the object. It is originally defined. And in our case, for the thin lens, you see easily you got it's equal to minus S prime over S here. Okay. Easy, right? It's also you already learned before. So now we will move to the diverging lens in order to see also the properties of that kind of lens. So it is different from the converging lens in the term of the position of the focal point, as well as the properties of that focal points. So converging lens, you have the two focal points with first focal point here and second focal point there, and all, both of them are real. But for the diverging lens, the diverging thin lens here, we see that if you have a parallel rays which are parallel to the optic assist, so after passing through this diverging lens, you see the outgoing rays diverge in this direction. So the outgoing rays diverge to this point, and this point is now here, not there anymore, right? Like the converging lens. So we have the second focal point is on the, we can say like on the left, in the same side with the incoming rays here. And up to, you see, the gathering point, in fact, you do the extension of the outgoing rays. So that's why we have the dashed line here, and F2 is virtual. Yes, so that's why in this case, the focal length, the distance between the focal point and the center of the lens is negative. So here you have a beam of rays parallel to the axis, passes through the lens, the rays diverge to a point F2. So just pay attention. And you may feel sometimes confused how to draw that. So don't worry, you just draw. This is the incident rays coming to the lens. So the refracted rays coming from this point and then in this direction. Here also in this direction. And you see the two surfaces of the lens distributes in this manner. We will discuss a little bit about that right after. So here, incident rays to this point, and then it reflects in this direction, you see. So the second focal point here you got is like in the same side with the incoming rays and virtual here. And for the first focal point, we see the incident rays converging towards to the first focal point, and then they emerge from the lens and parallel to the axis. So you see incident, yes, incident to this point, for example. So, and then it will come this way. I'm sorry, this text also cover this outgoing rays. And here we see, yes, coming to this point. Okay, and outgoing in this direction, the refracted one. Here, to this point, and refracted rays coming here. Okay, so that's how you can draw the outgoing ray by a diverging thin lens. So the F1, the first focal point. Okay, come back to a little bit far. The first focal point for the case of a converging thin lens, it locates in the same side with the incoming rays. And it was written, so F is positive, the focal length is positive. But for the diverging thin lens, the first focal point is not located in the same side with the incoming rays of the lens. So you choose the lens as the boundary, and then we see the first focal point and the incoming rays, they are not in the same side. So that's why you see here, this is virtual. It's something similar to the case you have the virtual object. So the virtual object, the incoming rays is here, but the object is another side. Yes, it's how you can draw and identify the virtual object, okay? And each point that the incident rays face the lens, and then you see the outgoing rays in this manner, okay? So here, we have the incident rays converging toward the first focal point F1, only toward because it's not truly converging to that. So you see, because it stopped at the incident rays may stop at the surface of the lens. And then after that, it is a story of the outgoing rays now. So we see incident rays converging toward the first focal point F1. They emerge from the lens parallel to the axis. Okay. These figures show some different examples of the converging lenses and diverging lenses. So A, you see meniscus with this side here. So the two surfaces, we see this direction. So the two center of curvature is located there. Yes, first center curvature and the second one center curvature for these two surfaces. And next to that, we have one convex and one plane, right? One is planar. So that's what you got, the plano-convex, plane and convex. And here we got the double convex. Yes, the double convex situation. And for the diverging lens, you see you can have double concave, okay, the double concave. And the center curvature is here for this plano concave. Here's concave and here's plano concave, and miniatures as well. So different types of lenses can be considered as the converging lenses or diverging ones, depending on the size at the center of the lens. So these three different lenses we just consider, even they are different in the shape. However, they has also the mutual or the common property is that it is thicker at the center than its edge, right here. And so you see thicker at the center than the two edges, thicker at the center than the two edges. Looking at the diverging lenses at different shapes, however, the center here is narrower than the two edges you see. Okay, so in conclusion, any lens that is thicker at its center than at its edge is a converging lens with the positive F. And any lens that is thicker at its edge than at its center is a diverging lens with negative F. So it's okay, it's clear for you why the converging thin lens or a diverging thin lens has positive focal length or has negative focal length, right? And also the way we can distinguish or we can classify what is a converging thin lens and what is a diverging lens. So depending on the thickness in the center compared with the edges of that type of lens. Okay, now we will move to the session 2.44, the Lensmaker Equations. So before we have the relationship between the object distance, image distance, and the focal length, now we will move to the Lensmaker Equations, which one shows the relationship among the focal length F, the refractive index N of the lens, and the radii of curvature R1 and R2 of the lens surfaces. And also for sure, it will relate to the object and image distance as well. So basically we have the Lensmaker, which shows the relationship also among these parameters of the lens itself. So that's what we call the Lensmaker equation. In order to see that, we will look at this figure. So this figure showing the ray diagram as well, right? So we have an object, PQ, in front of a lens. And here it is a curved miniature lens. And then you see the center of the lens is thicker than the edges. So for sure it is a converging lens. Also, if we look at the rays of light coming to this lens, and then they converge. So that's why we have the converging lens as well. And we see here the lens with the refractive index NB of the materials inside this lens. You got the refractive index or index of refraction NB, which is put inside inside some media with the refractive index NA and refractive index NC. So NA is the materials which includes the incoming rays from PQ. And then you see NB is the refractive index of the materials of the lens. And NC is the refractive index in this part, so of the materials, which includes the outgoing rays, finally to generate the image, the final image, P prime prime, Q prime prime. And looking in detail for this lens with the refractive index NB and two spherical surfaces with the two center curvature, C1 for this first surface, C2 center curvature for this surface, the second one. So the first one that is closer to the object, it is a thing we call the first surface. And the second one is the surface which is further from the object. Okay, we have the second center curvature, C2. And then we have the radius of the first surface, R1 and R2. Lê Hoàng Anh ơi, em nhắn lại vào nhóm chat ấy, bởi vì có một số phần cô đã để trôi, cô viết thêm phần text vào đấy nên là hơi bị trôi, có những bạn điểm danh muộn chẳng hạn ấy, thì em nhắn lại một lần nữa vào nhóm chat để các bạn có thể điểm danh lại em nhé. Nhớ note luôn cạnh bạn nào muộn nha. Cảm ơn Hoàng Anh và cảm ơn các em nhắn cho Hoàng Anh về điểm danh của mình nhá. Cô sẽ collect tất cả các cái thông tin. Okay, so sorry for this interruption. And we have here T is the thickness of the center of the lens here, T. And normally we consider T is very small, okay? And PQ, which is in front of this lens. And then now we will consider the formation of the image by using the refraction of a spherical surface we already studied last Friday. So PQ in front of this first spherical surface, right? So the incident rays like this one, it will be reflected. Sorry, refracted. I'm so sorry for that word. So it will be refracted, and then you see the refracted rays in the dash lines and gather here at the P prime Q prime. So it is not, sorry, it is not like a virtual one. They just want to notice with you about the, the image formed by the first one here. Okay, and then you will also have the final image which is formed by this system at the P prime prime Q prime prime. So S1 here is the object distance to the first surface, and here we have S1 prime is the image distance from P prime Q prime to this surface, and S2 and S2 prime as the object and image distance of the image, and so this object and this image to the second spherical surfaces respectively for these two. Okay, so step by step here, we have two spherical interfaces denoted by C1, so the center of curvature C1 and the radius R1, the center of curvature C2 and the radius R2, separating three materials with refractive index NA in this region, and B for the lens, and NC for this region, NA and B and C. And S1, S1 prime are the object and image distances for the first surface. S2, S2 prime are the object and image distance for the second surface, you see, for the second one and for the first one. And as the thickness of the lens is very small compared with this S1, S1 prime, S2, S2 prime, so we can consider S2 equals minus S1 prime here. Because in general, you also have if you have a system of the optical devices, so we normally have S2 equals D minus S1 prime. That means the next object is equal to the distance between the two optical devices minus to the previous image distance to the previous optical device. Now we will follow the refraction by the spherical surface. So we got NA over S1 plus NB by this materials of the spherical surface here with the material NB. So NB over S1 prime equals to the subtraction of NB and NA over R1, the radius of the first sphere. Sorry, this first spherical surface. Okay, so that's what we studied also last Friday together. And keep in mind, the refractive index of the material which contains that type of incident rays. So we got here incident rays in the material with the refractive NA. So that's why S1, the distance of the object to that surface, we got S1 in the denominator. And then the image is formed by this spherical surface, the first one. So we have also, the image is there. So that's why in the numerator, you have NB over S1 prime in the denominator, S1 prime corresponding to this material. And then on the right-hand side of this equation, we have the difference NB minus NA over R1, but it's related to the first surface. And for the second one, if we consider for the second one, similarly, you see S2 will be considered by this second surface. So that's why you got NB in the numerator and S2 in the denominator. So NB over S2 plus the outgoing rays in the materials NC here. So we got NC over S2 prime. And then on the right-hand side, similarly, you have the subtraction of the two refractive indexes, NC minus NB over R2. Pay attention to this relationship. So you will follow the S2 equals minus S1 prime. And we also do one assumption for like a simple case in which the lens, which consists of two spherical surfaces having only the refractive index NB equals to N, and it is positioned in the air only. So we consider that NA equals NC equal to 1. So if we assume only this simple situation, and then also following this relationship, and then you replace into these two equations we just provide, and then you will achieve to this 1 over S1 plus N over S1 prime equals N minus 1 over R1. And then for the second equation, it will be minus here N over S1 prime plus 1 over S2 prime equals 1 minus N divided by R2. So if you do the sum of these two formulas, you see this term will be neglected. So you got only 1 over S1 plus 1 over S2 prime equals N minus 1 multiplied by 1 over R1 minus 1 over R2, right? And you can write in general, because S1 is the object distance from the object to the first surface. So indeed, it is the object distance of the object to the lens. And S2 prime is the image distance from the image to the second surfaces. So we have also, it is the image distance in overall. So you see 1 over S plus 1 over S prime equals N minus 1 multiplied by 1 over 1 minus 1 over 2. So we see here, okay, this formula. Coming to the previous object image relationship, in which 1 over S plus 1 over S prime equals 1 over F. So it brings us to this formula, 1 over F equals N minus 1 multiplied by 1 over R1 minus 1 over R2. So here is a so-called Lensmaker equation. You see the relationship among the focal length, the refractive index of the lens, and the two radii of the two spherical surfaces which construct to the lens. So that's what we call the Lensmaker Equation. And also keep in mind here, we consider the lens is positioned in the air. So we got n-1 here. So if for the assumption, we don't do that kind of easy, we consider also like NA equal to NC equal to some kind of N, like NS means surrounding or NM means material surrounding. And the refractive index of the lens is NL for the lens. So then you can try this later on to see how this lens maker change. Like we can have like some kind of question like, if we bring the lens and put it inside the water, so how the focal length of this lens change compared with the case of in the air? Yes, so that's what something you should pay attention as well. Here we consider this Lensmaker equation for a thin lens when it is put in the air. Okay, I remind you again and again that. We have a figure showing you here to remind with you the sign rules. Yes, sign rules. Because if we follow the Lensmaker equation, 1 over f equals n-1 multiplied by the subtraction of the reciprocal of the radius here. And sometimes you may feel confused, right? Confusing about like R1 may be positive, R2 may be negative, for example. So how they can be determined for their sign of their polarity in the term of values. So in that case, remember we already studied together the sign rules. Maybe the first or the second lecture, I don't remember very well. However, we have that for the sign rules of the objective distance. So if the object is located in the same side with the incoming rays of the optical devices, and then the object distance is positive. And for the image distance, so the image must be located in the same side with the outgoing rays of the optical devices or of the surface when we deal with the surface last time. So it can be positive, otherwise it will be negative. And for the radius of curvature of any kind of surface is also depending on the position of the center of curvature. If the center of curvature is in the same side with the outgoing rays, and then it is positive. And if it is not, the center of curvature is not on the same side with the outgoing rays, and then it is -1. So here we go, we see. Okay, I will ignore that so that you don't feel a lot of information. So please look in detail at this figure. We have this lens, which is formed by the two spherical surfaces. So the first one, which is closer to the object, so we call that the first surface. Object is here, and from that it emerges, right, a lot of rays coming to this lens, and then after passing through this lens, this ray refract in this direction, and you see on the refracted rays converge at the image. So it is a converging lens we are considering, and the refractive index of this lens is m. Surrounding is air. For example, if we draw like this, that means surrounding is air. So the first surface, which is closer to the object, and we see the center of curvature is there for the first one. The first center of curvature is here, and the radius of curvature of the first surface, R1, is this one. So in this case, R1 is positive because C1 on the outgoing side of the lens. Okay. Now look at C2. The second surface is here, and the second center of curvature is here. So we have the radius of curvature of second surface is like this one. So C2 is on the ingoing side of the lens, or it is not on the same side with the outgoing rays of the lens. So R2 is negative. So when they ask you to find the focal length of the lens and the values of the absolute value of the radial curvature of the lens surface, they also provide the value is like 10 centimeters, for example, and the refractive index of the lens is 1.52. So you already know the magnitude value for the radii and also the value of n here. So very easy, we just apply this type of equation and only pay attention to the sign of the values of the radius, right? So R1 is positive, so R1 is equal to 10 centimeter. However, at R2, after our explanation and discussion together, but only I is the one who speaks. However, I know that you understand that as well, and you also have the same idea with me. So R2 is negative, right? So we just follow that and pay attention here. You got R2, you see, minus 0.1, right? It's meter. We do here, we convert everything into the SI unit, so you got meter. If you don't really like the SI unit, for this formula is okay for you because N is only the refractive index, so we can say like unit list. So in overall you have F and R in the same unit term. So you can use 1/10, but don't forget only that. Also, sorry, I didn't note the final values for you. Okay, I just forget. However, you can you can yourself do that. Okay, and then you got the value of F. F is 1 over these values, and then you have the values for the focal length. And easily you see it is positive, right? So it is a K conversing lens. Now, in order to finish this session of thin lenses, we will have the graphical methods for lenses. Here we have the graphical methods for lenses. So two kinds of lenses are considered here: converging lens and diverging lens. So converging lens F1, first focal point is here, second focal point is there. Diverging lens, first focal point is on another side, and second focal point is on this side. Pay attention, and the reason we already explained, right? So I do hope that after this part you are very clear about that. You have no doubt, no confused issue. If the lens you study from high school, I already know that. So here we just do the remind and so the review, because it is a very important component in the geometric optics as well. So we have the object PQ, and PQ for the is located in front of the lens. Okay, for the two types of lens here, we consider three special rays of light. So the first one, parallel to the optic axis. Yes, you see, parallel to the optic axis. So it meets the lens. So we will draw until this point. And that's why you normally you will have, okay, how can I do that? I want to show you that. Let me think. Let me think, how can I draw that? Okay. Yes, I want to escape a little bit in order to add something here with you. What I didn't do that this morning, but I will do this afternoon because I want to show you. Yes, perfect. It's normally you use in the high school like this one. So I will make it shorter so that it don't disturb the, it doesn't disturb the image. And then I will make it bolder. Okay, cool. Let me see if you have also the diverging lens here or not. No, we don't have. Okay. So this one is fine as well. And for this here. Okay. Yes, when we do the class online, we don't have the. Okay, cool. A little bit not so pretty. However, you understand that, right? Okay, cool. So sorry, I'm drawing very bad. Here we go. Yes. A slideshow. Perfect. So you can use this symbol of the conversing lens like this one. You see, there is a line passing through the center of the lens, and then you use these two arrows to show that it is converging. Or you can use this one to show the line passing through the center of the lens, and then you use these two symbols. So please don't draw so ugly like me when you use in your exercise. However, we do that. We have that for the symbol of the diverging lens, right? Yes. So the first ray parallel to the optic assist, and then it passes through the second focal point for the converging lens. And for the diverging lens, you see here, it passes like it's emerged. Yes, it emerged like from this point, the second focal point, but it's not rimmed. That's why we need to do this kind of dashed line. Only from the incident point here to the outgoing part is rimmed with a solid line. And the second ray of light passing, which passes through the center of the lens, so it goes straight. And so it goes straight for both cases. And the third one, the third ray passes through the first focal point for the conversing lens. Or you see, in this case, it passes the lens, but seems to do what? The first focal point only. So that's why this part, you draw the dashed line. Pay attention. And then this ray meets the diverging lens at this point, and then the outgoing rays parallel to the optic assist, you see here. So we consider three special rays of light: a ray parallel to the assist, emerge from the lens in a direction that passes through the second focal point f2 of a converging lens, and appears to come from the second focal point of a diverging lens, you see here. It emerged from the lens in a direction that appears to come from the second focal point of a diverging lens. So that when you draw with the diverging lens, pay attention, there is the dashed line because it's not rimmed. The real rays of light only from the object to the lens, and then reflected from the lens like this one, you see. So this is only the virtual one, and we do with the dashed line next to the solid line part here. A ray through the center of the lens emerge at essentially the same angle at which it enters and along essentially the same line. Okay, we can say this for short, like a ray through the center of the lens, go straight. Okay, go straight. And the third one, a ray through the first focal point f1, or the ray proceeding toward the first focal point. So this ray through the first focal point only for the case of the converging lens. For the diverging lens, the first focal point is not in the same side with the incoming rays, which is virtual here. So it's just proceeding toward. So that's why you have the solid line for the incoming rays, and you draw also the dashed line here to show that it proceeds toward this first focal point. And then the incident rays come to the lens at this point, and from this point it will refracted parallel to the optic assist. So in order to find the yes, it emerged parallel to the assist. In order to find the image here, all the refracted rays meet at this point, which is the image. Here, all the refracted rays, the outgoing rays, you see, they don't truly intersect, right? So that's why we do the extension of the outgoing rays like this one, and then you will find the image is here. So in this case of the diverging lens, always if you have a real object, it will produce the virtual image. And for the converging lens, it depends on the location or the position of the object compared with the focal point, the first focal point. And then different types of image will be formed. So this is the overview of different cases for the converging thin lens. For the diverging thin lens, you can do it yourself as well. And pay attention, here we see object O is outside focal point, and always you have the real image, inverted one, you see, okay? And if we shift the object O closer to the focal point, to the lens, so closer, when it gets closer, the image I, when it's real, you see, it's real, you see here. And see, when you locate, you bring the object even closer to the focal point, and then image ring, and also you get further, you see, further away. And if the object is located right at the position of the first focal point, and then the image is formed at infinity here. And for that case, we don't mention about the real or virtual image. We just say the image is infinity. And for the object O is inside the focal point, so get closer, we see the outgoing rays like this one, and then they gather also virtually at this point. So the image is virtual and larger than the object and erect. So pay attention, you have some pair. So we have some pair of what to say about the property of the image, the real and virtual. Real, virtual, erect, or inverted. Okay, and larger and smaller and same size, okay, we don't mention anymore. And even you can have the virtual object here. So in that case, we see the light rays, instead of diverging from this image, you see here the light diverge from this object, but here is the light converge right on the lens, you see here. So when we have this case, so the object somewhere here, and all the extension rays coming to this object. So we got the virtual object with the incident rays like this one. They meet the lens, and then you see the outgoing rays. So the first incident rays parallel to the optic assist, so outgoing rays, it refracts also through the center, the second focal point at 2. And this incident rays passing through the first focal point to the lens, and then it will refract parallel to the optic assist. And the third one, yes, I'm so sorry about the orders, 2 or 2 or 3, it doesn't really matter, right? This one passes through the center of the lens, so it goes straight, you see. And then finally, we see virtual object, at this case, produce a real image, because the image in this case is formed by the intersection of the real outgoing rays. So we have only this case summarized in this slide, and then you should draw yourself to confirm that as well. So we spend some time on the thin lenses, and we have here some example. What we are going to do with this is just also I will discuss with you. You should draw yourself also in the paper, because the formulas when we use the mathematics is just to calculate the exact value in terms of the mathematical point of view. But the phenomenon we want to describe, we need to use the drawing. So that's why they also have here the question. Draw the rays to find the image and mention the properties of the image. So when you want to mention the properties of the image, I would like to tell you again, the image is real or is virtual, or is erect or inverted, or and larger than or smaller than the object itself, and also like equal size as well. So this exercise or this example, sorry, you should do it later on at home, and you see here different position of the object, 50 centimeters. So you see farther than the focal length, right? Even larger than 2 times. All of you are in the major of ICT or cybersecurity or in applied math, etc. So basically, you studied quite carefully the physics, and we know also like if S equal to 2F, right? You have this type of special condition. So S prime also equal to 2F. And in this case, you have the same size. So also we consider the relationship between S and 2F, 2 focal lengths as well. So here 50 centimeters, so larger than 2F, 20 centimeters, so equals to the focal length. So when the object is located right at the focal point, the first focal point, because it is positive here, 15 centimeters, that means you shift the object closer to the inside the focal point and closer to the lens. And final one is the virtual object, when the object at the distance of minus 40 centimeters. So it is what here in this case, you see the object is here. So that's how you can draw the rays of light. So in order to calculate, because they ask you to find the image position and the magnification. So in order to do that, you follow the object image relationship for the thin lens. And then you know S already, you know F already, you can easily find the image distance in each question. So it's easy for the calculation. And you got the lateral magnification M equals minus S prime over S. And then you just replace the values you find. In each case, the image is erect or inverted, larger than or smaller than the object. So we have this value. In each case, you can easily find that one. So in order to find the values, it's not so complicated, because you just follow the equations of the object image relationship as well as the lateral magnification for the thin lens. The most important thing I really want you to do is to draw. Okay, so you can do it later on at home. If we are doing the offline class instead of the online class, normally I will ask the student to do it at the class, and then I will collect also your solutions in order to see if you understand and can practice this properly or not. Also, if some of you do it well, I also add some bonus point for the midterm test. Here we are doing the online class. So this part I just discussed with you like this one. You should do yourself at home. Okay. And for the second type of example, it is for the case we have for the diverging lens here. So they provide you a beam of parallel rays spread out after passing through a thin diverging lens, as if the rays all came from a point 20 centimeters from the center of the lens. You want to use this lens to form an erect virtual image that is 1/3 the height of the object. Question A, where should the object be placed? Where will the image be? And B, draw a principal ray diagram. So when we are in the geometric optics and when you are in physics in general, the drawing is a critical task for you to describe the phenomenon. I want to emphasize that. So here, when you read this example, which can we obtain? Which parameter can we obtain right now? If we see a beam of apparent rays spread out after passing through a thin diverging lens, as if the rays all came from a point 20 centimeter from the center of the lens. So which bring you which type information? So any ideas? You know, do you guys who want to answer my question? Which quantities shows in the first sentence of the problem? No one? Okay. Nguyễn Hà Phương Linh, are you here? Nguyễn Hà Phương Linh?
Yes.
Yes, cool. So if you read this problem, which information can you deduce? For example, the first sentence here, which show you which type of parameters, which type of quantities of the lens?
This is a diverging lens.
Cool. So you know that we are dealing with the diverging lens. Perfect. And 20 centimeter here is which quantity of the lens?
The ray.
The ray?
The ray.
Yeah, okay. So when we're talking about any kind of lens, which quantity characterized for the lens? Please tell me which quantities, which parameters described or characterized for the properties of the lens. Like if I tell you any type of lens, which parameter you are waiting for to describe that lens?
The image.
The image is what will be formed from the lens. However, we must we would expect also some parameter of the lens, the intrinsic property of the lens. When I tell you, okay, I have a diverging lens or a converging lens, so you will curious about which parameter of that lens. The image is what we are going to do later on. If you have some object, and then by using the lens, you will have the image. I totally agree. So the formation of the image depending on the property of the lens as well. So which parameters of the lens will show the property of the lens? So if it is a little bit difficult for you, I would like to move to the previous example. Here we see find the image position and magnification for an object at each of the following distances from a converging lenses, right? So yes, like Ling, right, just mentioned, we wonder about the image position. We do agree. Any kind of optical devices, when we use that, we want to know how the image is formed, how the lateral magnification will be. However, the property of that lens we want to know is here you see the focal length. The focal length is like something which is characterized for that lens. You will agree with me, Ling?
Yes.
Okay. So now, when we read like a long sentence with the parameter here, with the number 20 centimeter. So what does this mean for this lens? Diverging lens, agree? Yes, it is a diverging lens. So what is the meaning of this value, 20 centimeter, for this lens?
It's the focal.
The focal what? Pay attention, we have two focal of the lens, focal point and focal length, right? So you remember the focal length? What does this mean about the focal length? What is it?
This is the focal length from the center of the lens to the focal point.
Perfect. And in this case, we have the focal length of this lens. What is the value?
20 centimeters.
Are you sure 20 centimeter for the diverging lens?
10. It's 10.
Okay. So and also it is positive or negative for the focal length of this lens? Positive or negative? You wonder, right? So Ling wonder a little bit. Yeah, okay. So do you guys who has any idea about the sign of this focal length in this case? If you guys who want to speak out, you can either raise your hand or you can speak out as well. So no one, right? So I will call some student. Thái, I remember a student called Phùng Đức Thái here. Okay, Phùng Đức Thái, are you here?
Yeah.
Did you do the I mean the admission exam with me last week, last Saturday?
I'm sorry.
Oh. So you did you do the exam with me last Saturday? Sorry. No, not you, right?
I don't remember.
I mean last Saturday we have like an exam for the high school pupil, sorry, who want to enroll in our university, and I was also in an exam with.
No, that wasn't me.
Yeah, okay, maybe it's Vũ Trọng Minh Thái, right?
Yes.
Yes, it's you. Okay, so I'm asking Phù Minh Thái. Okay, now Thái. Coming back to this question, Ling mentioned that the values of 20 centimeter in the first sentence of this problem shows us the focal length of the lens, and she said that the focal length of this lens is 10 centimeter. Do you agree with her?
I'm not sure.
You are not sure?
Because as if the rays all came from a point 20 centimeter from the center of the lens, so I would think that the point here is a source of the light.
But yeah, so please read on the whole sentence.
Okay.
Yeah.
Parallel rays spread out after passing through.
So,
okay.
Okay. So here, yes, you can think also about it is the source of the light. I totally agree. And yes, we also have some answer from Đào Duy Mạnh Hà here. And in order to answer this question, that's why I tell you you should draw. Because if you draw, yes, if you draw, I will.
So I guess it is focal point, second focal point after the length.
Yeah, you see here. Yeah, you're right. Like if you have a parallel rays applied to the optic assist here, and the outgoing rays also appears to come from a point which is 20 centimeter from the center of the lens. It is what we see at this figure, right? You see the incoming rays parallel to the optic assist, and the outgoing rays seems to come from a point. So yes, it is the source. I agree with you, Thái. It is the source of the rays, but it's not the object. In this case, it is like the second focal point. Yes, and that's why Đào Duy Mạnh Hà mentioned in the chat box with us, f equal to minus 20 centimeter. So Hà, could you please also speak out with us about your opinion? Thank you, Thái. Đào Duy Mạnh Hà, why you got f equal to minus 20 centimeter?
I don't know how to explain.
Yeah, yes. The important thing is that sometimes we know the answer, but it's like a little bit complicated to explain to the others, the people, and what we need.
I see.
Yeah, what we need from this course, like even you learn already this knowledge before at the high school. However, we should like be able to explain everything in English, for example. So here, in order to do that, let me check if I have also the figure, but no. So I will do the escape a little bit. Wait a little bit away. A couple of minutes and we will be clear about that. We don't have the board here, and that's why sometimes it's a little bit inconvenient. Okay, cool. So I will paste it here. Yes, perfect. So an important task when you are studying everything in English is to, oh, no, it's not this one. So I'm so sorry. This next one. The important task when we're studying everything in English is to be able to understand the problem. When you read the problem of the exercise, you must be able to understand what they are talking about and what is what. And then you can do the, you can solve the exercise. Yes, so in order I will shift. So sorry, my computer is a little bit slow. Come on, come on. Cool. Here we go. I shift this out a little bit to leave some space for this image. Okay, very good. So I will show the slide again. So if you read this problem, a beam of parallel rays spread out after passing through a thin diverging lens, as if the rays all came from a point 20 centimeters from the center of the lens. So it's not the source actually. In fact, it's like you have the emerging rays here, and they all seem to come from this source, like Thái mentioned. But here is like the image, right? It is the image of this outgoing rays. So when we read this first sentence, it describes the focal length of this diverging lens. So a beam of rays parallel to the axis, after passing through a thin diverging lens, as if all rays came from a point here. So you see they emerge, they spread out here. They spread out as if they all came from this point. So this is a second focal point. And like Đào Duy Vĩnh Hà wrote in the chat box, from that we can conclude F equals, if the magnitude, so the absolute value is 20 centimeter, but here it is a diverging lens. And that's I also explained with you in the beginning of this lecture today. It's not real, right? This point is virtual. That's why F is negative for the diverging lens. It's not like the case of the converging lens in which F is real. The focal point is real. So we have the positive focal length, but for the diverging lens, it should be -1. Maybe Phương Linh before she has some kind of confused between the focal length and also the radius, so they divide it by 2 and then she got like 10 and this. But pay attention here, it is exactly what I show you in this figure. So when you read this, please make a draw. And then you will easily find that, okay, it is a focal length. And it should be negative because you see as if the rays all came from this point. So we got F equal to -20. So you got F equal to -20. And they also ask you, like, you want to use this lens to form an erect and virtual image. Erect, when you have erect, that means F is, M. Okay, I will ask some students, what does this mean when we say the image is erect? So now another Thái, Vũ Trọng Minh Thái. Okay, hôm nọ bạn Thái đi coi thi cùng với cô trong buổi thi kiểm tra tuyển sinh đầu vào của trường mình. Thế nên là cô chỉ nhớ có bạn Thái, mà không biết là bạn Thái nào, cô mới nhìn tên các em, cô thấy bạn Phùng Đức Thái, cô gọi Phùng Thái thôi. Bây giờ cô hỏi bạn Vũ Trọng Minh Thái. Okay, Vũ Trọng Minh Thái, please. When you have the image they've mentioned here is erect, so what is the conclusion from that? This clue can bring us to which kind of information? Chọn Minh Thái, are you still here? Okay, I see your mic is on. Good. And then where are you now?
I'm here.
Okay, cool. So the information they bring here, the image here is erect. So it relates to which quantity? How can we conclude the image is erect? From which quantity?
Can you speak again?
Okay, we see here in this problem, they mentioned you want to use this lens to form an erect image. So when we see the clue that it is erect, which can be deduced from that? It relates to which quantity? Or another kind of question is, how or when can we say that the image is erect? You use which quantity to say that the image is erect or not? The image is erect or inverted. We conclude from which quantity? From which quantity? So okay, forget about that question. Forget this. I asked you, Thai, and also other guys again, another question. When can you conclude that the image is real or virtual? So we have the property of the image is real or virtual. We all agree with that, right? So how can we conclude that the image is real or virtual? And then similarly, I will have another question, like when we can conclude the image is erect or inverted. So we have two questions. So when can we conclude that? From which quantity? Okay, so Ha mentioned here is based on the direction, and based on direction is when we draw. I agree. However, from the quantity, so maybe Thai missed that type of information, but Ho Quang Anh also mentioned in the chat box that M is positive. So yes, I want to emphasize with you, I want to remind you that if we calculate the lateral magnification, yes, Lan Dang also, he also chat faster than me. Lateral magnification M equals minus Y, sorry, the original, I'm so sorry, original formula. Lateral magnification will M equals Y prime over Y. So in which Y is the height of the object and Y prime is the height of the image. And if they are in different direction, so Y prime will be negative. And in that case, if M we calculate and M is positive, we say that the image is erect. M positive, sorry, M negative, and then we conclude the image is inverted. It is about the direction of the image compared with the object. And if we calculate and we got the image distance S prime is positive, and then we say the image is real, right? And if you calculate and you got negative S prime, and then we conclude the image is virtual. It is what we need to say. So in this example, they mentioned we got an erect image, but virtual one. So erect, that means M is positive is what I want to ask you, and the answer I expect is that you will say the lateral magnification is positive for this case, and it is virtual, so S prime is negative. You see here, and it is 1/3 of the height of the object, so M equal to 1/3. Yeah, is what we have. So finally, we see here M equals minus S prime over S. So pay attention, I write here already minus S prime over S, but coming from the original formula, it is Y prime over Y. And in the case of the lens, we will have it is equal to minus S prime over S. Here we go. Y prime over Y and equals minus S prime over S, and it is equal to 1/3 here. And F, the focal length of this diverging lens, we can derive that from this first sentence here. F equals minus 20 centimeter. And you follow the object image relationship, 1/S plus 1/S prime equals 1/F. And then finally, you will find the values of S and S prime, you see here. So the object be placed in this way and the image is here. Wait a little bit, I have a phone call, and meanwhile you can have a break. Em có thể nghỉ giải lao một chút xíu nhé, đến 2-3 phút rồi cô có cú điện thoại xong người ta sẽ quay lại. Đấy, bây giờ chúng ta đang trong giờ giải lao một chút và cô cô nhắc lại với các em một chút về phần này. Thì hôm nay chúng ta vừa mới trao đổi với nhau xong ấy, thì cô cũng biết là lúc học online thì nó rất là kiểu 3 chấm, tức là cảm giác là các em ngồi trước máy tính xong rồi nghe cô giảng bài nó cũng rất là mệt mỏi ấy. Thì nhiều phần mình cũng sẽ không cảm thấy nó dễ tiếp thu. Đấy là cũng là một sự rất là thật thôi, ai cũng bị vấn đề cảm giác cái buổi học nó hơi buồn khi mà các em ngồi học online, ngồi trước máy tính, không ngồi cùng bạn bè xung quanh, không có mọi người, và đấy là vấn đề. Và những bạn nào mà đã học tốt vật lý rồi thì những cái phần mà các em học ở đại cương bây giờ nó cũng không quá xa vời với tụi em lắm, nhưng mà rất là quen thuộc, chỉ khác mỗi phần chính cho những phần đến bây giờ, đó là các em học một hồi trước cấp 3 các em học tiếng Anh, bây giờ các em học tiếng Việt, bây giờ các em học tiếng Anh thôi. Tuy nhiên là có nhiều khi thì các em hoàn toàn biết những cái vấn đề này bằng tiếng Việt, nhưng lúc mà chuyển sang tiếng Anh xong tự nhiên các em cũng cảm thấy nó hơi bị lạ, chẳng hạn như những câu hỏi trong bài này, nếu mà chúng ta dịch nó ra xong mà các em hiểu đúng thì các em thấy không có gì cả, rất là dễ dàng. Một bài tập có lẽ là chúng ta sẽ học từ hồi lớp 11, lớp 12 gì đấy, cô cũng hình như lớp 11 các em học phần quang lớp 11, và đây là quang hình. Thế còn những phần mới của trong phần quang của chúng ta học sắp tới nó là phần giao thoa rồi nhiễu xạ để chúng ta học tiếp theo sau. Và thậm chí cả giao thoa thì phần đầu em cũng đã học rồi. Các em học về phần thí nghiệm của Young chẳng hạn, Young đấy. Thế nhưng mà chúng ta sẽ đi sâu hơn vào cả những phần liên quan đến cường độ, hay là ở đây chúng ta sẽ học cái cách mà để chứng minh các công thức em đã biết. Thế nên là nếu mà để các em làm tốt những phần này ý, thì cô khuyên tụi em là các em cứ đọc, đúng là bao giờ cũng thấy cái đọc kỹ là lecture note trong phần textbook, tuy biết là dài nhưng mà họ viết rất là cẩn thận chi tiết, thì các em sẽ nhìn những cái kiến thức nó rất là logic và chịu khó phải nắm được các cái từ vựng bằng gọi là tiếng Anh học thuật đấy, scientific English, thì các em phải cố gắng các em mình nắm được này. Và khi mà các em làm bài tập vật lý, bất cứ bài tập nào các em nên vẽ hình. Đấy là điều cô khuyên các em. Các em vẽ hình các em sẽ miêu tả được cái hiện tượng đấy. Đó, và các em chịu khó làm bài tập. Không cách nào khác, khi mà học cái môn vật học tự nhiên thì hiển nhiên là bài tập là cái phần mà giúp chúng ta vận dụng. Chứ còn các em nghe xong các em cũng sẽ cảm thấy nó quên rất nhanh. Thậm chí cô có thể nói đi nói lại các em những phần kiến thức như những gì mà chúng ta vừa trao đổi ấy. Nhưng rồi nó cũng bay khỏi đầu chúng ta rất nhanh nếu chúng ta không luyện tập nhá. Thế, đấy là một phần cô chia sẻ với tụi em một chút. Và có những gì các em cảm thấy khó khăn thì các em có thể chia sẻ với cả cô cũng như là anh Hoàng Anh là TA của lớp mình, thì các em có thể gửi email cho với các cô, ví dụ như cô ơi phần này các em không hiểu như nào đấy. Nhưng quan trọng là chúng ta cũng có những cái khó khăn chuyện trong học khi chúng ta học online. Các em vừa mới từ lớp 12, lớp cấp 3 chuyển sang đại học mà học một lúc rất nhiều kiến thức như này chẳng hạn, một buổi học hơi dài ấy, thì cũng mệt. Và thực sự hôm nay cô có hỏi bạn Thái, bởi vì tuần trước đúng là có gì cô vừa đi coi thi cùng với bạn Thái cho cuộc thi kiểm tra kiến thức đầu vào của trường mình. Thì trường mình ngoài các giám thị là các thầy cô giáo, các cán bộ công nhân viên trong nhà trường, thì cũng có mời một số bạn sinh viên tình nguyện đủ một số tiêu chuẩn nhất định để các em cũng sẽ tham gia cùng. Thế thì các em giúp đỡ các giám thị trong phòng thi thôi, các em không gọi là giám thị của phòng thi, nhưng các bạn sẽ là tình nguyện trong phòng thi. Thì hôm đấy cô tình cờ cô gặp Thái và cô hỏi Thái là thế là em là sinh viên năm mấy và em đang học như thế, thì cô bảo thế em vừa mới học môn quang học hôm qua phải không? Thì hôm đấy hôm thứ Bảy, hôm thứ Sáu tuần trước chúng ta vừa học quang cùng nhau. Thì Thái cũng chia sẻ đúng thật là bạn bảo là đấy nha, có cả Thái ở đây nhưng cô không cô trao đổi luôn. Bạn cũng bảo là học cảm thấy hơi bị chán nản, hơi buồn khi mà lớp học chúng ta học online như thế này, rồi trước màn hình máy tính các thứ như thế, thì nó cũng là cái tình huống mà chúng ta phải thích nghi và khắc phục thôi. Còn cô cũng rất là hy vọng là các em vượt qua những cái khó khăn về việc mà tình hình chúng ta phải học online, nhưng mà để đảm bảo cho sức khỏe, để đảm bảo cho là các bạn F0, F1 các bạn tuy không được đến gọi là ra ngoài, các bạn vẫn có thể tham dự vào được này, và việc lây lan nó không quá nhiều. Còn chúng ta cũng ai cũng mong cái chuyện là sẽ được quay trở lại trường đấy. Thế thì cô cũng chia sẻ những cái khó khăn của các em gặp phải, cũng như là các em cũng hình dung được là một thầy cô mà ngồi giảng bài như thế này cũng cảm thấy nó boring như thế nào, đúng không? Đấy, chúng ta cùng cố gắng. Đấy là phần cô chia sẻ trong lúc em giải lao một chút. Bây giờ chúng ta lại quay lại cái bài của chúng ta. Cô sẽ escape để cô xóa cái hình này đi. Tức là khi bao giờ các em phải hiểu được đề người ta nói gì, muốn hiểu đề người ta nói gì thì các em phải chúng ta nên không nói các em phải nghe là cứng nhắc quá, các em nên follow các kiến thức và hiểu được đúng đề. Nghĩa là các em phải cần có một cái vốn từ về mặt khoa học nhất định này, và các em cần kiến thức nữa, đúng không? Hiển nhiên. Thế, so here we see in this case of this example, we see this object put in front of this diverging lens, and it is what we draw in the final part. But in the first part, when we see this example, I would like to advise you to also make the drawing. So like the previous figure I just delete, you should draw, okay, a beam, a parent rays, passing through a diverging lens. So you draw this diverging lens, and then the rays spread as if the rays all came from this point. So you know, it is the focal length of this diverging lens, and it should be minus 20 centimeter. Because we know that that sky focal point is not real, and so for the diverging lens, the focal length is negative, so you got his value. Also, we can conclude from the erect and virtual image. So the other quantity, like lateral magnification, is 1/3 and positive. The image is virtual, so S prime is negative. So you see the consistency in this case. We have the real object, the virtual image, and then you have the erect in the direction of the image. And you can find the value of the object distance. image distance. It is what we need to do in the geometric optics to see the relationship of the object distance, the image distance, the lateral magnification, right? M, the lateral magnification, and then you make the drawing here. You put the object distance. You know also the focal length already. So 2 times, you see object distance 2 times of the absolute value of the focal length. And pay attention, the F1 is here and the second focal point is here. The first focal point related to the incoming rays is what I want to emphasize. And the second focal point related to the outgoing rays. The diverging lens, everything is like the opposite order. So that's why we need to pay attention. So from this object, we have the ingoing rays like this one. So they meet the lens. And then the outgoing rays, you see, the first rays parallel to the axis, and then it refracts, and the extension of it will pass through the second focal point, but only it is the virtual. That's why you need the dashed line here and the outgoing rays there. The second rays you draw coming to the lens and proceed toward this first focal point, and then outgoing rays parallel to the optic axis. The third one, which passes through the center of the lens and goes straight. And then for that, you will find the image, which is the intersection of the outgoing rays. So the outgoing rays, they don't meet each other. Really, they don't meet each other, you see. Truly, they don't meet each other. So that's why you need the extension part. And then all of them gather at this point, which is the image. So we see the image is virtual, you see here, and erect, because it's the same direction here. So that's how you can draw this. And it's not so complicated, right? So is this okay for you for this example? And you feel like easy for this previous part related to the lens? Some yes, some no, maybe. Okay. So now we will stop the thin lens here, but I spend a lot of time with you on the thin lenses because they are the core component of all the next, the upcoming optical devices. So here we have the cameras first. Well, try your best, okay? I know that you feel very tired, you feel a little bit bored during the online class, and also for the physics, yes, for the physics, and you will feel a lot of information, also like the equations, and just listen to me like this is also a little bit tired, but try your best, okay? Let's go. So we have here, the next session, we talk about the cameras. So we study the camera, which is very popular, which is also very familiar with you guys, right? So the key components of the cameras for sure is the system of the lens. And also inside you have also this aperture. This one is an aperture in order to tune the numerical aperture. Yes, you see the aperture control diaphragm. We will discuss on that as well. So the cameras coming from the Latin word, that means a room or enclosure. Yes, and then your picture will be kept here, okay? If you have the film, and if not, you will have nowadays you just store it in the memory and then you will read it later on. But basically, the main component, the key, is a converging lens. A converging lens, but it also consists of some lenses, and then overall we have the positive focal length, which is a converging lens. And there is a shuttle here to open the lens for a prescribed length of time. So you have a shuttle, you have a light sensitive recording medium. So it can be the CCD, the charge coupled device array, or a photographic film. So it is like the screen placed in order to record the image formed. Okay, so we have here the elements of lens, the shutter, the real image is here, which is the CCD array here, and here's the object. So the function of the elements of lens we got here also to adjust for different object distances. The image distance is changed by moving the lens in or out, we see here. And for this part, the lens formed an inverted and usually reduced and brilliant image, and in the plane of the CCD array, you see here. And we can, as we mentioned, that you can change the focal length. Yes, the focal length can be changed, can be adjusted, right? So we see here the focal length of a camera, which is an important factor as well, an important quantity. Everything related to the lens, we need to consider for the focal length. It is some quantity characterized for the lens. It's also the question I asked you and discussed with Phương Linh, right, previously. Like when they show you one sentence to describe about the focal length of the diverging lens in the previous example. So here, different focal lengths can be used in the camera in order to capture the angle view you want. So here, narrower angle, right? And here, wider. So here you can see clearer the object, and here you see the overview of the picture. So it's like the springtime because you see the flower everywhere. You see in this picture, and maybe it's like in Europe somehow, like this picture. We do put it as an example here. So from the focal length equal to 28 millimeter, for example, 105 or 300 millimeter here. So, so we can see if you use smaller focal lengths, and then you can capture wider angle. You see here, and larger focal length, narrower. You see, so we see the larger the value of f, the smaller the angle of view. We got here. And we have different kinds of values of focal length for the cameras. A lens of long focal length, or we say of telephoto lens, will give a small angle of view and a large image of a distant object. You want to observe some object which is very far away, like the paparazzi, they already do, right? So you need a telephoto lens to capture them. And then you can see the large image of that kind of distant object. And the price you need to pay is about the small angle. So depending on your purpose. And if you use a lens of short focal length, so you will have the small image and also wide angle view. And it is called the wide angle lens. So you have the photo lens, telephoto lens, or the wide angle lens. It depends on the purpose. And as usual, in order to form the image, we also care about the lateral magnification. For this part, right after the cameras, when we study another kind of optical device, we will care also about the angular magnification. And here for the lateral magnification, m equals y prime over y equals minus s prime over s. So we have m equals y prime over y and equal minus s prime over s, because we base on the cameras is also the converging lens. So that's what we have. The next quantity to describe the camera lens is the f number. So you have the focal length f, and now you have the f number. So the f number is to show the light gathering capability of the lens. And normally they will be expressed in the terms of the ratio f over d. It is called the f number. So you see f is a focal length, and big D here, what is this one? So I come back to the previous slide. This one, you see. This part is an aperture control diaphragm, and you will have this aperture with a diameter d. So f number equals the focal length f divided by the aperture diameter d, in which f is the focal length Big D is the diameter of an adjustable lens aperture, or the diaphragm. I just show you, and it is nearly circular hole. So, for example, if you say a lens with a focal length f equal to 50 millimeter and an aperture diameter d of 25 millimeter, so the f number is the focal length divided by this aperture diameter, so equal to 2. So the f number is 2. So we say that we call that an aperture of f over 2. And the light intensity reaching the film, or the CCD, the reason we just show the screen, we say, is inversely proportional to the square of the f number. So the intensity I mentioned with I, big I here, is proportional to 1 over f number square, like this one. Okay, 2 here means square, not okay. When I denote like this, you may confuse with it like 2 times. Okay, so I will write like this one, over power 2. You see, 1 over f number power 2. So inversely proportional to that, so 1 over that value. And 1 over f, that means it will be proportional to the, so I also proportional to d, the aperture diameter square. Right, correct, yes. We will have also the system like we call the zoom lenses and projectors. So zoom lens here means that we not only have one lens, so for those who play with the cameras, you know that very well. So it is a system of the different kind of lens also in order to have the variable focal length we change. So here, for example, if you want to have a long focal length, you combine a converging lens and a diverging lens together, and they are close to each other like this one, and then you have a long focal length. And for short focal length, you put this combination with the distant distance, and then you have the short focal length. So that's what you have the zoom lens. And for the projectors, if we don't study online like this, and if you study offline at USDH, normally we will use a projector to show the slide, right? And you can also present something using the Skype projector. Yes, so the projector also very similar to the camera itself. Now we will look at some small example to practice a little bit about the cameras. So first is about the photographic exposures. So related to the exposure, it relates to the aperture diameters. So here we mentioned a common telephoto lens for 35 millimeter camera has a focal length of 200 millimeter. Its f-stops range from f over 2.8. So the f number here, you see the aperture number is 2.8, f over 2.8, and here f over 22. They ask you to find the aperture diameters. So easy, you have focal length, you have this range, you can deduce the aperture diameters. And for the corresponding range of image intensity, so keep in mind the image intensity is inversely proportional to the f number. So for that, we can also use related to the d values. So you'll find the aperture diameters in this range, 200 millimeter divided by this number they provide. So minimum to maximum, and the intensity also proportional to d. So you just take this kind of ratio and make the square, and then you see the range of that. It is one example related to the opening, the change in the aperture diameter in the f number. And the second one is also the exercise. However, it's this one, then the 34.47 is in the old version of this textbook. This textbook now, maybe this exercise will be changed. But it is one popular job to find the proper camera lens. For example, here, the picture size on ordinary 35 millimeter camera film is 24 millimeter multiplied by 36 millimeter. The focal length of lenses available for this camera typically include 28, 35, 50, so we call that the normal lens, 85, 100, 135, 200, and 300 millimeter. So these focal lengths change in these values. Which of these lenses should be used to photograph the following objects, assuming that the object is to fill most of the picture area? A building 240 meter tall and 160 meter wide at a distance of 600 meter. So at this distance, that means you know S already, right? And this size, you know about the size of the object. And here you know the size of the film, which is also to be the image. And the question B is similar thing. So the idea, main idea is that we need to find the focal length. We need to find F, provided that we know the S and we know already this relationship that brings you to the lateral magnification M. So a building 240 meter tall and 160 meter wide, if you want to locate it in this film, so the lateral magnification you follow from this original equation, M equals Y prime over Y, and you replace 24 millimeter here divided by this, this Y with 160, and then you got this value. However, for this kind of lens, you can also use M equals minus S prime over S. This one is the original definition. Always it is for the lateral magnification. We have that. And here in our case, we have this formula for the lens. And S is equal to 600 meter, right? So here is 600 meter. While the range of the focal length is only like around millimeter. So S is very large compared with F. So if we follow this formula of the object image relationship, 1 over S plus 1 over S prime equals 1 over F. So because S is very large, so 1 over S is very small. So you can neglect this part, and we see that S prime more or less approximately equal to F. So we can deduce F equal to S prime, and then we follow the lateral magnification, M equals minus S prime over S. So you know the value of M. You know also the value of S. You can deduce the value of S prime, which is close to the values of focal length. So we find the values of focal length is 90 millimeter. So you should choose this lens, right? In order to fit most of the picture area, so we choose this one. And similar for the second case, I don't do that anymore. You can do that at home as well. So the principle is that the idea is to choose the various values for the focal length can be chosen using this principle. Okay. Now we will move to the next optical device. I will let you like 1 minute to pause so that you don't know. You will feel a little bit relaxing, okay? Before we come into the eye. Okay, now we will study the eye from the optical point of view. So showing you here in this figure is a diagram of the eye. So step by step, we will see different components: the cornea, the aqueous humor, the pupil, the iris, the crystalline lens, the ciliary muscle, which hold the crystalline lens, the vitreous humor, you see the vitreous humor, the optic nerve, which to interpret the image. And we have the fovea centralis, you got also the retina. In order to be able to observe the image, so the image should be, in order to be able to observe the object, this is what we want to observe. The image should be located at the retina, right? So step by step, we see the different components of the eye. So we have here the size of the eye is a 2.5 centimeter diameter sphere, and the cornea here is a tough and transparent membrane. So you got that kind of cornea. Is a tough and transparent membrane outside our, like just when everything enters our eyes, is past the cornea first. And the aqueous humor, which is a liquid region behind the cornea. And the crystalline lens here, which is a capsule containing a fibrous jelly, hard at the center and progressively softer at the outer portions. So this crystalline lens is a lens to form the image. Yes, is what. And which is held in place by the ligaments that attach to the ciliary muscle. So the function of the ciliary muscle is very important. Like it can be contracted so that the lens will become more convex and to decrease the focal length. If you want to do the accommodation, we will study about the accommodation process as well. But when we want to do that, we need to change the focal length of the crystalline lens, and that is a function of the ciliary muscle here. And the vitreous humor is the aqueous humor. Is the type of the liquid also, and the values of the refractive index of both the vitreous humor and the aqueous humor. So the aqueous humor, which just behind the cornea here, the refractive index is around the water, you see, 1.336, and the crystalline, which is not homogeneous, and the refractive index is around 1.437 something. And behind the lens, the eyes is filled with a thin watery jelly. So it is what the components of our eyes. And most of the refraction of light entering the eye occurs at the outer surface of the cornea here. And the refraction at the cornea and the surface of the lens will form the real image we recognize. So the image must be formed somewhere, right? So it is formed at the retina. The image is formed on the light sensitive, lining the rare inner surface of the eye. So it's similar, or it's like the film in a camera. And here is the SCM, the scanning electron micrograph, which shows the retina rows and cone in different colors, so in green and in blue, here we see. And this is not taken by the normal cameras. The normal cameras we use is using the optical light for the camera. We use that kind of optical light range. So normally it's like the visible range. So for the visible range of light, we cannot observe something which is very small. So we will use another kind of rays, which is from, like, for example, here we use a scanning electron microscopy. So the SCM. So for you guys who work in ICT, in data science, in cybersecurity, for example, or in applied math and so on, you don't face with this SCM a lot. But for those who study this morning for the measure of AMS or the measure of the MSD in the PMAP, when they want to study something which is very tiny, they need to do the SCM, the scanning electron microscopy. And here is one example. And we've got the rod cones here, an array of miniature photocells, which have to send the image and also transmit it via the optic nerve to the brain, so that the brain will understand, okay, this kind of object is what. Also, we have the foveal centralis, which is about 0.25 millimeter in the diameter. and we have the acute vision in it, with it that in the place of the image. And also the iris, as I just described with you earlier in the previous slide. I show you the position of the iris, which contains an aperture with a variable dimension. And the pupil is also very important of the eye, right? When we want to check the health of somebody, normally we also observe the pupil of their eyes as well. So the pupil opens and closes to adapt to changing light intensity. And the receptors of the retina also have intensity adaptation mechanism as well. We have here the accommodation process in eye. Yes. So the eye adjusts to different object distance S by changing the length F of its lens. So this process, like when you want to see the object at different location, you need to change its focal length, and then for that, it is a so-called accommodation. And keep in mind that the length to the retina distance S prime never change. Yes, because the image must be formed exactly at the location of the retina. So S prime does not change, only we change F. Because if you want to fix the object is there, which is closer or further, and then you need to change F, right? Because S prime also fixed. S also fixed, depending on the object. You can say, okay, object, come here, right? Normally we can do all, but basically the S is also fixed. So if we want to observe some kind of S, we need to change the focal length of the lens as F here. And if we observe something which is at infinity, and then in that case, the ciliary muscle is relaxed. And when you observe some closer objects, and then the tension of the ciliary muscle surrounding in the lens will be increased, and the ciliary muscle will decrease, and then the focal length decrease as well. So that is what about the accommodation. So that's why sometimes you feel your eyes tired, sometimes you feel your eyes relaxed as well. And we have the concept of the far and near point, like what you usually study in the high school for the CC and the CV point. It is what you use in the high school. And here we call that the far and near point. So it is the extremes of the range over which this thing is possible. That means you can observe the object clearly in this range. And normally for a perfect eye, for the normal one, the far point is at infinity, and the near point is normally for 25 centimeter. And that and the near point, the position of near point depends on the amount by which the ciliary muscle can increase the curvature of the crystalline lens. So we see in this table the receding of near point with age. So increasing the age, and you see the near point also further as well. You see here from 7 when we were very young, and then very far away when we get old. And it is the presbyopia. When your muscle do not work well anymore, and then we face this problem. So the presbyopia is the phenomenon in which the near point recedes with age, because the crystalline grows throughout a person's life. So pay attention on that as well. Now we will dealing with some defects of vision. We hope to have a normal eyes in observing object. However, normally we do not have that. So our eyes also got some kind of defect. And here in this part, we will deal with some kinds of defect of the of vision. So for the normal eyes in which the near point is around 25 centimeter and the far point is at infinity. So if we observe something at infinity, so the rays from a distant object, so that means that the object is at infinity. And when it reaches the eye, like this one, you see here, the cornea and also the crystalline lens. And the outgoing rays focuses at the retina, like this one. So it's perfect, right? However, for some kind of the eye, the rays from distant object, when it goes through the eyes, is located in front of the retina. So that means we cannot see them right. So it is a case of the myopic or nearsighted eyes. Nearsighted means we cannot observe something which is at infinity. So that's what we will call the nearsighted. In this case, the eyeball is larger than the radius of the curvature of the cornea. Here, the cornea is too sharply curved, and then the rays focus in front of the retina. The cornea is too sharply curved, so the rays focus in front of the retina here. It is for the myopic eye. So if the eyeball is larger than the radius of curvature of the cornea, and then the rays from an object at infinity are focused in front of the retina we see here. So the most distant object for which an image can be formed on the retina now is nearer than infinity. So we cannot observe some object at infinity anymore. So here, showing you, we have the distant object, which seem to be like very far away in infinity. And then you see the image is here. It's not on the retina, but it is in front of the retina for the case of myopic eye. Okay, the incoming rays, and then they are refracted and gather at this point. So in order to correct the myopic eyes, because we want to observe the very far away object, so correcting the myopic eye involves using a diverging lens, or we say the negative, because the focal length is negative, to move the image closer to the eye than the actual object. Because the actual object we want to observe is at infinity, but the myopic eye cannot observe that. So we use one tool, which is a diverging lens. And then it will have to create another image. And then our eyes will look at this image. In fact, this new image becomes the object of our eyes. So here we see the distant object is here. And then we use this diverging lens to form this image. And this image becomes the object of our eyes. And we see the incident rays passing through this diverging lens. It will refract in this direction, right? And the outgoing rays from this lens gather at this point, which is the image of the lens, and becomes the object of our eyes. And then you see finally the outgoing rays are located at the retina. And that means we can observe that image here. We can observe this image of this lens, which becomes the object of our eyes now. So finally, with the help, with the assist of this diverging lens, we can see this object, we can say that. So here we got a diverging lens, and the diverging lens creates a virtual image. And in order to be able to observe that, it should be inside the eye's far point here, for example. Because different people have different eyes far point, and the myopic eye, normally the far point is not at infinity. So by checking the far point of this person, we can find the property of the diverging lens to be used. When we say the property of the diverging lens, that means we're talking about the focal length of that lens. Yes, and then the image focused on the retina, and we can observe that clearly. Good. Another case of the defect eyes is the hyperopic, or we say the far-sighted eye. So in this case, the eyeball is smaller than the radius of curvature of the cornea. So here is the eyeball. Right. And then the rays from an object at infinity are focused behind the retina. So the retina is here, but the image is there. So behind the retina. And for sure, we cannot observe that, right? Because it's not in the right screen, it's located behind that. So if the cornea is not curved enough, so you see the eyeball is smaller than the curvature of the cornea, and then the rays focus behind the retina. And in order to fix this type of problem, before we talk about like fixing this type of problem, we must say about the problem of the hyperopic eyes. It is what we saw, and also if we put any kind of nearby object, for example, at the 25 centimeter, it is the near point of a normal eye, right? However, for a hyperopic eye, if we put that kind of nearby object, when we observe this object, in fact, the image focus behind the retina, not on the retina. So that means we cannot see the object which is close to our eyes, right? So correcting a hyperopic eye, and that's why also the people say the far-sighted eye, because this eye cannot see the close or the nearby object. It can only see the far-sighted object. That's why we call the far-sighted eye. So in order to correct the hyperopic eyes, that means we will use a conversing lens. So, and also the note here is a positive, that means the positive focal length, which forms a image and formed by this converging lens, and we will put somehow to make it the virtual one and larger than the object, and also in the up or beyond the near point, because the near point of this hyperopic eye is quite far away. It's not 25, but it's like 60 or 70 or even 100, 200 centimeter. So we use a converging lens, and then the converging lens creates a virtual image at or beyond the eye's near point. And then you can observe that the image will finally located on the retina. So we see here this object, the actual object, located quite close to the eye. So we don't observe that. We cannot observe that. So we need this lens. So the rays coming from this object to this lens will be refracted. And then we do the extension of the outgoing rays. We find this image and it comes to the eye. You see, and it will be refracted here to right at the retina. You see. So it is the problem of correcting the defects of vision related to the lens system. Yes, it's what we will see right after in the example. Also, our eyes can have the astigmatisms as well. So for the astigmatisms, it related to the shape of the object. So in this case, so everything related to the cornea, right? The surface of the cornea is not spherical, but rather than more sharply curved in one plane than in another. So people who has the astigmatism eyes, they will see the object in a very strange shape. For example, the horizontal lines may be imaged at a different plane from vertical lines. So here we see we have the object with this shape. So here we denote the horizontal one and the vertical one. The horizontal one in this plane, we see, and it can be focused at this position. However, the vertical one is here, you see. So you see the shape of eye bones or lens causes vertical and horizontal elements to focus at different distances. So that's what we can see, a very strange object, right? So, and the astigmatisms can be corrected by the use of a lens with a cylindrical surface. So here, so in this case, we remain the horizontal position. So it does not change the horizontal element. It changes only the vertical one because it is curved in the vertical, but not in the horizontal one. So you see now the vertical and the horizontal part of this object in the same distance. So you can observe that. Good, right? So when a cylindrical lens with its axis horizontal is placed before the eye, and then the rays in horizontal plane is unaffected, but the additional divergence of the rays in the vertical plane causes these to be sharply imaged on the retina. Yes, it's what we can fix the problem of the astigmatism eye. And some eyes also face not only one among those we just mentioned, but it can face like both astigmatism and myopia or hyperopia. Yes, so in this, we need to consider about the spherical power, the cylindrical power, and an angle to describe the orientation of the cylinder axis when we want to fix this kind of problem. And lenses for vision correction are usually described in terms of the power. When you go to the doctor to check your eyes, and then they provide you some kind of eyeglass to correct your defect. So normally we will talk about the power of the lens. So in order to do that, we need to check the reciprocal of the focal length in meters, and then the unit of the power is diode. So we got here, for example, a lens with f equal to 0.50 meter. In order to check the power, you need to do the reciprocal of the focal length. So 1 over f, so it equals to 2 diode. And if a lens has minus 0.25 meter, for example, and then the power is minus 4 diodes. So we know that. We have one example to practice a little bit about how to correct the farsightedness. In this case, we have the near point of a certain hyperopic eye is 100 centimeter in front of the eye. Find the focal length and power of the contact lens that will permit the wearer to see clearly an object that is 25 centimeter in front of the eye. So you see, truly hyperopic because the near point is 100 centimeter in front instead of 25 centimeter, right? And they ask you to find the focal length f and the power of the contact lens, which permit the wearer to see clearly an object of the 25 centimeter in front of the eye. So we will draw this system. You see here, the object you want to put is 25 centimeter away from the eye. However, our eye, in this case, cannot observe that. So that's why you put a converging lens. So converging lens, here, the distance between the converging lens and the eyes, d equal to 0, because it is a so-called the contact lens. So the distance between the contact lens and our eyes is 0. And the object, the signal or the incident rays coming through the converging lens, and then it will refract, right? And we see the image here forming by this converging lens. And this image now becomes the object of the eye. And then finally we got this final we will have like the final image somewhere else. So here you see the image here, this image. This image should be located at this point, the near point here, 100 centimeter. So we have the object, which is in front of the contact lens, and then it will form the first image, which becomes I denote here object 2, that means now it becomes the next object of the eye. This object is object of the contact lens, right? And it will form the first image, and then it becomes the second object of our eyes, and then our eyes will form the second image of the retina. So S1 is equal to 25 centimeter, and S2 to our eyes here is equal to 100 centimeter. That's what, if you have some object which located at this distance, and then this eye can be able to observe. So that's why you have here S2 equals 100 centimeter. And the relationship between the next object distance and the previous image distance is that S1 prime equals D minus S2, in which D is the distance between the two optical devices. So you have S1 prime equals D minus S2, in which S2 equals 100 centimeter. So finally, we can know S1 prime already, and then you can find the focal length of this lens, right? Yes. So I also prepared the solution. You can follow that. I just want to discuss with you in detail for that, and then you can find this value. Okay. And for the myopic eye, it's the same, but in this case, we use an eyeglass lens, and eyeglass, so it has a distance 2 centimeter in front of the eye. So also you should write this. We say like the diagram of the lens system. So the object, which is infinity for the lens and also for our eyes, and then the eyeglass lens forms the first image, which it becomes the second object to our eyes. And in order to be able to observe this object, that means the object must formed at the far point. So you see, this eye is very strange. It can be only observe the object, which at the farthest point is 50 centimeters away from the eyes. So very bad, right? You cannot look far away, you see. So you do the same. We have S2 must be equal to 50 centimeter. You know S1 is infinity. S1 prime has a relationship with S2 is here, because what we need to find is about the focal length of the eyeglass lens we use. So we focus on this part. The next part only dealing with the eye. And then you have S1 prime equals D minus S2. And in this case, because we use an eyeglass lens, so we have the distance 2 centimeter. So you can find S1 prime, you know S1. So F will be equal to this value. Very easy. And then you see it should be diverging, right? So you can do that at home. I just want to emphasize with you about that. Okay. Yes. So I will take a glass of water and then we continue. Before that, I will move to this so that you can look in detail for that as well, for the example. Okay. Cô có chị lấy một cốc nước, em có mệt lắm không? Chắc là cũng hơi mệt nhỉ, hơi oải, thì cố lên nhá. Okay, so let's continue. Now we move to another optical device, which is called the magnifier. So the magnifier is something which, like the person who want to fix our watch, normally they will use, yes, in order to look in the small component inside any type of watch, right? So here, for example, showing you in this figure is an inchworm, which lies in the leaf like this one, and we look at this type of inchworm. So we see here another quantity, which is theta, yes, and the height or the size of this inchworm is y, and we will have the so-called angular size. So new terms here. The angular size, which is the size of the image on the retina, depends on the angle theta subtended by the object at the eye. So here. At the distance of the near point, we consider, so 25 centimeter. So we put the object is at the near point, so 20 centimeter for the normal eyes. We only consider the normal eyes. And the object subtend at an angle theta at the eye. And we got theta equals y over 25 here. We have the so-called a magnifier or magnifying glass, a simple magnifier, which is a converging lens, can be used to form a virtual image that is larger and farther from the eye than the object itself. And that is the so-called magnifier or magnifying glass, or simple magnifier, all the names are the same. So we see here, we have a magnifying glass or the magnifier. You put the object right at the focal point. So the image will be formed in infinity, right? And now our eyes look at this. We look at this one. We see theta prime here. So theta prime is also the theta prime here, theta prime. So we see, which is parallel, so here is theta prime. With the appearance of the magnifier. So with a magnifier, the inchworm can be placed closer than the near point, and the magnifier creates an enlarged upright virtual image. Yes, they are parallel here. So we got now in this case, when we use a magnifier, it forms an image at infinity. Pay attention, we put the object upright at the focal point, and the angle subtended at the magnifier now is theta prime. Is theta prime, and theta prime will be equal to y divided by f. Okay, this angle is the same, so we got here y divided by f. So we have the new quantity, which is the angular magnification. Before we study only the lateral magnification, and here we have the angular magnification m, which is the ratio of the angle theta prime with the magnifier to the angle theta without the magnifier. And then we have this following formula. Okay, where is that? So we see m equals theta prime over theta. So pay attention, theta prime is when you use the magnifier, and theta is without the magnifier. And then you got m equals theta prime over theta, and you replace y over f divided by y over 25. And you got 25 over f here, which is the angular magnification of this magnifier. So they denote the angular magnification with a big M and the lateral magnification with a small m. So we got the lateral magnification and the angular magnification, big M like this one. Okay, we're clear about that. So now we will move to the next optical devices. Microscopes and telescope. Microscope, that means we want to observe something very small. Telescope, we want to observe something very far. So the microscope, so normally the guys who study the measure of LS in the LS department for the MSD, for the PMAP, they will need to use that a lot in their lab. Here we see the elements of a microscope. So we have the light source, the object is put here, we have the objective lens, and then we see the image is here, and then we got the eyepiece here. And you want to observe, you put the eyes here. And for the optical point of view, we see the objective, the eyepiece of this microscope, and here's the object. The objective has two focal points, f1 and f1 prime. The eyepiece has also two focal points, f2 and f2 prime here. And normally the object is positioned here, for example, quite close to the first focal point of the objective. And then we see the image is formed, inverted, real and inverted one. So, and it becomes the object to this eyepiece, right? So, and then we see finally the final image is here, Y prime, I prime here. So the eyepiece will use this image I as an object and creates an enlarged virtual image I prime. And you see it's still inverted compared with the object. So we see here S1, the distance from the object to the center of the objective. S1 prime, the distance from the image to the center of the objective. Here, F1 and F2 are the focal lengths of the two objective and eyepiece. So the components of the microscope contains an objective lens with the focal length F1 and which forms a real image. And a second lens, which is the eyepiece here, as an it acts as a magnifier with a focal length f2, and it can make a enlarged and virtual image. So this image of the first objective here must position very close to the first focal point of this eyepiece, so that the final image is enlarged and virtual one here. And the principle of that is that of this microscope is that the object O, which is very small, is placed just beyond the first focal point of the objective. This lens is close to this object, so that's why we say that is the objective to observe this object here first. And it is very close, the object is very close to the first focal point, so we see S1 is very close to F1. More or less S1 is approximately equal to F1. So it will form a real and enlarged image I. And I lies just inside the first focal point F2 on the eyepiece, or we say the ocular. And the eyepiece acts as the magnifier and forms a visual image I prime of I, you see here. So I prime, in order to be able to observe this, that means I prime must be between the near and far points of the eye, and then we can observe that. So we have in this case, the microscope in order to observe something very small. So we use the angular magnification M, which equal to the product of M1, the small M1 multiplied by the big M2. That means the lateral magnification of the objective, because the objective acts only like the normal lens here, and the magnifiers here. So that's why we have the angular magnification of the eyepiece. So angular magnification of this microscope equals to the product of the lateral magnification of the objective multiplied by the angular magnification of the eyepiece, M2. And then you replace M1 by this value, S1 prime over F1. and it is the lateral magnification of the objective lens. And we have S1 prime is the image distance for the objective lens here. So you got 25 centimeter multiplied by S1 prime over F1 multiplied by F2. So it is the angular magnification. And for this microscope, yes, and in a micrograph, the image also forms on the CCD. The CCD array films, like we mentioned in the camera. And for the telescope, yes, it is similar to the microscope, only except that it is used to view large objects at large distances. And many telescopes also, they use a curved mirror instead of the lens for the objectives. So in that case, you have the reflecting, yes, the reflecting telescope. And for what they use the lens, it is called the refracting telescope. So see, you see the ISP here, the objective lens here, and then we see, we can observe that. And pay attention, we observe something very far away. So that's why we have the incoming rays are parallel to this objective, and then it's formed like the image right at the second focal point of this objective, right? And they also arrange the system so that the first focal point of the eyepiece is in the same position with the second focal point of the objective. So F2 and F1 prime at the same position. And then we will see that the image, final image is also at infinity. And for that, you have here this angle theta prime. So step by step, we also discuss about that. So lens is used as an objective, in this case for the astronomical telescope. And in this case, we have the refracting telescope, or we say the refractor, because it's based on the refraction. That's why I also discuss with you very detailed for the part of the refraction, and also what we formed the image by the surface, by the lens, because they are the key component for the incoming path here. So if you look at an astronomical telescope, and then the objective lens forms a real reduced image eye of the object. The object is far away, like the star, for example, and then you form here, and then the main object is at infinity. So this image here is at the position of the second focal point of this objective. I is at F1 prime. And I now becomes the object for the eyepiece lens, and which we have to form an enlarged and virtual image of I. And I prime will be at infinity. And I here is at the the first focal point of the eyepiece at F2. So this kind of arrangement makes that the sum of F1 and F2, the two focal lengths, the sum of that is the length of the telescope, because it is the distance between the two objective and eyepiece. And the angular magnification in this way is equal to minus F1 over F2, which is the ratio of the angle subtended at the eye by the final image I prime, we see theta prime here, and to the angle subtended at the eye by the object only when there is no supportive, so you have theta here. So that's what we got, minus F1 over F2 for that. Yes, also you can use a CCD to position the image location. And you can have also, if the case, if the mirrors is used for the as an objective, we have the reflecting telescope. So why they choose to use that one? Because we can also solve the problem of the chromatic aberration and also the spherical aberration. It is easier to fix rather than compare with using the lens. So here is an example like of the interior of the Gemini North telescope with the reflecting surface, in which 8 meters in diameter for the objective mirror. Okay, and for that we end the chapter number 2 here. And today we will move on to chapter number 3 a little bit. So I would like to mention that we will have like, I think 10 minutes more today. Yes, because we have also some break, and yes, so enjoy a little bit. So we will move to another properties of the light, in which we deal the light as a wave. And then we will study the interference and the diffraction of this course, and then we finish the part of the optics. So in order to learn about that, first we will deal with some concepts or some definition about the interference and coherent sources, two-source interference of light, and the intensity in interference pattern. When we have the interference, we must pay attention to the intensity as well, like the bright patterns and the dark fringe, how the intensity will be and how we can recognize them as the bright fringe or the dark fringe. And we will study also the interference in some condition, like in the thin films or in the Michelson interferometer. The Michelson interferometer, we have this system in USDH. If you can do the practical work dealing with the optics part, it's also very interesting for you to use the Michelson interferometer in order to check the values of the wavelengths of the source. So to begin with, oh yes, very beautiful picture, right? It was captured by me in Paris, like in my business trip in 2019. So you see very beautiful blue color, and you can understand why the sky, the very beautiful blue sky. And after finishing the first chapter, you can be confident to explain why the sky is blue, right? Due to the scattering, right? And also why the cloud is white. And here you see some bubble. Yes, it is close to this one is close to Notre Dame. And then you see this kind of beautiful color fringe here in the short bubble. It is this picture I captured from the book, this one done by myself, okay? So we see this beautiful color here. In fact, it comes from the interference. So that's what we are going to study now. So to start with that, we need to understand about the term interference. So interference and the verb is interfere. It related to the meeting of some waves. So the term interference refers to any situation in which two or more waves overlap in space. And it comes from the principle of superposition. In physics, normally you will deal with this principle of superposition a lot. When you study the fundamental physics 1, you study the mechanics with Dr. Bun from the Institute of Physics, as I remember well. If any kind of object, any kind of particle can be exerted from various forces. So you will find the resultant forces by taking the algebraic sum of all other force. So that is the so-called superposition. Or when you study the electricity part with Dr. Hưng from Vietnam National University, and also when you study the charge, which is put surrounding by other charges. So the electric field from the other charges act on this charge. Also, you do the superposition, that's kind of principle. So here, when we deal with the interference in the term of the wave, the principle of superposition is applied in the waves in this way, in this manner. When two or more waves overlap, the resultant displacement at any point and at any instant is found by adding the instantaneous displacements that would be produced at the point by the individual waves if which were present alone. So any wave you can mark by, oh, I'm so sorry, I jumped too fast, sorry. Yes, I want to type here. Okay, so we have in some case you have the wave, which also a wave always involved with the change of the displacement over time as well. And when the two waves come to any point, so at this point, at this instant moment, we consider it will be the sum of the instantaneous displacement of other sources of the two waves. So it is the principle of superposition. And now we will see the interference in 2 or 3 dimensions. So the light waves can, and in fact, they do travel in 2 or 3 dimensions, right? As can any kind of wave that propagates in a 2 or 3 dimension medium. So if we take this snapshot of this wave, here we have a snapshot of a single source S1 of the sinusoidal waves. So for example, we have U equals A multiplied by psi omega t minus kx. For example, you have this kind of function for the wave in the sinusoidal function. And we see the spreading of this wave. And then we see also some wavefront produced by this source. Here, the wavefront. So from S1 is spread in one direction here. And the blue circle shows here is the wavefront. And the distance between the two adjacent wavefront is 1 wavelength, right? So the wavefront, the crest of the wave at the frequency f and separated by 1 wavelength lambda. So you see from here to here to here to here, each they has the separation of 1 wavelength here. And the wavefronts move outward from the source S1 at the speed v equals f multiplied by lambda. And if the waves are 2-dimensional, so we draw the circles to present the wavefront. But if they are in 3-dimensional, so we will use a sphere, right? So in this case, if the waves propagate in 3 dimensions, so the circles represent spherical wavefronts spreading away from S1. Here we do the snapshot. So that means the circles now represent the spherical wave in 3D. And in optics, the sinusoidal waves are characteristic of monochromatic light. So chromatic, chrome, that means to show the color, and mono, that means only one color. That means you have the monochromatic light, only one frequency, right? We have the terms of constructive and destructive interference in the interference and coherence sources part here. So we will try to finish this part only. Okay, just try our best. I know that you are very tired now. So do I. Okay. We have 2 monochromatic sources of the same frequency and with a constant phase relationship. So they are said to be coherent. So coherent sources, that means they have the same frequency and they have a constant phase relationship. And the coherent waves are we are dealing with the light, right? So that means coherent light refers to the waves emitted by 2 such above sources. So that means coherent sources will produce coherent light when we are dealing with the light. And if we consider 2 sources of equal amplitude, equal wavelengths, so that means same frequency. And in this case, we consider the waves are transverse with the same polarization along the y-axis here. And they also positioned equidistant from the origin. So the origin is here and the 2 sources are here, equidistant, you see? So each source will generate the waves. For example, S1, we see the blue circles. S2, we see the green circles, okay? And spreading out. So at any point in the space, will be the adding, yes, the wave here will be the adding of these 2 waves at this point. So if we consider point A, which lies on the x-axis, or if we consider any point on x-axis, the wave lives at S1 and S2, you see, arrives at A in phase, because you see, and the x-axis is symmetric, yes, between S1 and S2, so they should be arrived and at any point on x-axis, same phase. So the total amplitude at A will be twice of amplitude of each individual wave. And if we consider point B, so in that case, we count what is the distance. So from S1 to B, we see the wave front here. So H is one wavelength. So blue, you see the blue circle. 1, 2, 3, 4, 5, 6, 7. So 7 lambda. And from S2, you count the green. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So we see the distance from S2 is exactly 2 wavelengths greater than the distance from S1 to B. Because here 9 lambda and here 7 lambda. And a wave crest from S1 arise at B is exactly 2 cycles earlier than a crest emitted at the same time from S2. Okay, because here only 7 lambda, that means it corresponds to 7 cycles. Here 9 cycles, so 2 cycles earlier than from S2. So the total amplitude at B is also twice the amplitude of individual wave. So it is a so-called constructive interference. So here we got the case of constructive interference. When waves from 2 or more sources arrived at a point in phase, they reinforce each other, and the amplitude of the resultant wave is the sum of the amplitudes of the individual waves. It is for the constructive interference we are dealing with here. If we look in detail for that, if you point B, so R1, 7 lambda, R2, 9 lambda. So we have the relationship, we do the difference here, R2 minus R1 equals 2 lambda. So in general, we can say that it is equal to m lambda for the constructive interference. So for the constructive interference, the difference between the distance from the 2 sources to any point must be an integral numbers of the wavelengths. In the case the sources in phase, because here we are dealing with the in phase sources, and also you can have like the out of phase sources, for example, and then it will be different. So for the constructive interference to occur at point P, for example, the path difference R2 minus R1 for the 2 sources must be an integral multiple of the wavelength lambda. And pay attention, in this case, the sources in phase. And now if we look at point C, R1 equals to 9.75 lambda, R2 equals 7.25 lambda. So we do the difference between the 2 distance, this will be equal to minus 2.50 lambda. So in this case, you see the difference between the distance R2 minus R1 equals m plus half of lambda. Also, m is the integer number. So for that case, we got the disruptive interference when we consider the sources in phase. Pay attention for this formula. If the sources are out of phase, you will have the reverse situation. So for disruptive interference to occur at some point P, the path difference R2 minus R1 for the 2 sources must be a half integral multiple of the wavelength lambda. Okay, we have that. And we do the locus upon that point. You will have here at A and at B, which lies in this curve. The waves arrive in phase and interfere constructively. And these anti-nodal curves in red mark positions where the waves from S1 and S2 interfere constructively. So the locus of all this point is the antinodal curve. And for example, if we move to the point C, now at C, the waves arrive 1/2 cycle out of phase and they interfere destructively. Okay. And we got here m equal to 0, plus, minus 1, etc., which is the number of the wavelengths lambda, by which the path lengths from S1 and S2 differ, because you have R2 minus R1 equals m multiplied by lambda, or equals m plus half multiplied by lambda. Here you see these 2 formulas. So that's why it is the number of wavelengths lambda by which the path lengths from the S1 and S2 differ. So in this figure, red curves show all the positions where the constructive interference occurs, and that are the so-called anti-nodal curves. And on each curve, the path difference R2 minus R1 is equal to an integer m times the wavelength. And in the nodal curves, which in fact we don't draw here, but for example, this point C, and then it will be the curve between the nodal curves, and which are the curves that show when destructive interference occurs. So we see that. For that, we also end this the lecture today here. We will continue with that next Friday, and then a little bit tired because next time we will need to finish chapter 3 and also the next chapter of the diffraction. So we will do our best. Are you tired?
Yes, indeed.
Đúng thế, cô hiểu các em rất mệt, cô cũng biết là các em mệt. Very okay. Cô cũng hiểu mà. Rồi chúng ta cố gắng đây. 3 months of studying physics in high school is not even equal to 1 afternoon of studying physics at in your stage. It happens to you everywhere, not only in your stage. My students, that when you go to the university, especially for the fundamentals or like the general knowledge, you will study with the, longer time, so much more knowledge. And what you study at the high school is prepared for that. So when you get older, when you are now become an adult already, your brain can be able to do that. It is also the practice. Cô hiểu rằng là đúng là chúng ta học ở đây thì nhiều kiến thức trong thời gian lại học khoảng 2 tiếng, 3 tiếng. Rất nhiều kiến thức, và thực ra những kiến thức các em đang học bây giờ là kiến thức đại cương, nên nó cũng nối tiếp với những gì các em đã học ở phổ thông thôi, và bây giờ nó rèn luyện chúng ta khả năng là học tập trung hơn này và nghe nhiều kiến thức hơn này, hơi vất vả hơn đúng không? Rồi dần dần chúng ta sẽ quen dần, thế chúng ta mới trở thành người lớn được chứ. Và các em cố gắng đọc thêm textbook. Cô khuyên các em dành thời gian đọc các cái textbook các thầy cô gửi, vì là trong textbook tuy là nó rất là dày, nó rất là dài, nhưng mà viết rất dễ hiểu và các em sẽ thấy cái logic ấy, và có rất nhiều những ví dụ liên quan đến thực tế ở đó, thì các em đọc sẽ nó đỡ buồn hơn so với việc ngồi mà nghe giảng như thế này, mà nó cũng hơi mệt mỏi với chúng ta. Thế nhá, cô sẽ hẹn gặp lại các em vào thứ 6 tuần tới. Chúng ta sẽ khá vất vả vào ngày hôm đấy với việc là chúng ta học nhiều hơn này, chúng ta có bài kiểm tra nữa, nên là chắc là các em sẽ khá là căng. Đầu tiên cô định kiểm tra vào hôm nay này, bởi vì kiến thức kiểm tra chúng ta rơi trường 1, trường 2 thôi thì nó sẽ đỡ mệt hơn. Tuy nhiên là thầy cô vẫn hy vọng chúng ta kiểm tra được offline thì nó sẽ tốt hơn về mặt đánh giá ấy. Nhưng mà cũng hơi khó khăn, thì nếu mà buổi tối các em học xong đến khoảng tầm thêm tiếng nữa, xong rồi các em kiểm tra thêm 1 tiếng nữa, cô cũng đang thấy điều đấy hơi đáng sợ. Nhưng anyway, nếu mà hôm đấy quá chúng ta sẽ nhìn ra tình hình thế nào. Thế nhá, bye bye cả lớp. Các em còn có thắc mắc gì không hay trao đổi gì với cô không?
Bye bye cô.
Ok rồi, bye bye các em. Thế nhá, bye bye các em.
Cô ạ.